Welcome to this crash course on information retrieval. Today we're going to talk about test collections. My name is Sebastian, and as always, if you have any questions, remarks or suggestions, please feel free to write me an email. The topics of today are as follows. We're going to first look at some existing test collections and look at what is a test collection. Then we will see how to create your own test collection by running your own annotation campaign and some techniques that are information retrieval specific to be able to actually create such judgment annotations that we need for our information retrieval evaluation. And then last but not least, we're going to look at analyzing biases. So this is on one hand social biases that are concerned with learning from text, and then on the other hand a more technical position bias that is induced in passages and documents. The need for datasets, in my opinion, is very clear. So machine learning is driven by data, and every task needs some sort of task-specific dataset that models what we want to achieve. And for empirical evaluation, if we want to evaluate a model's effectiveness, for example, is our system better than the baseline according to some metric, we need data to be able to make this judgment. And most of the time, but of course not always, we also need data for training or fine-tuning a pre-trained model. And in many cases, the more data, the merrier. But again, with the caveat that we need also to focus on the quality of the data. So the more quality, the merrier as well. And there are many different tasks in machine learning and the different subfields of computer science, which means there are many datasets for various tasks. However, the more specific you drill down to a certain task, the scarcer the datasets usually become. And a great hub for text-based datasets is created by Hugging Face and gives you a nice overview of all the different tasks that people are currently trying to solve and work on. In information retrieval, the setup, if you recall from our evaluation lecture, is the following. We have a ranked retrieval result from some retrieval system that we want to evaluate. And on the other hand, we have known judgments for a given query. We have a pool or a set of documents or passages that contain labels that tell us if this document is relevant to this given query. And this pool of judgments does not necessarily cover the whole list, and if we have missing judgments, we have to consider them as non-relevant. So now, in the evaluation lecture, we looked at how to use judgments to produce metric scores, and in this lecture, we're going to look at what judgments are available and how to create those judgments. Existing IR test collections are the foundation for all information retrieval research, because without test collections, we would be totally in the dark of how good our systems are actually working. A test collection is usually an umbrella term for the following set of data. It's used for offline evaluation with a fixed set of documents or passages, a fixed set of queries, and a fixed set of judgment pairs that cover some, but not necessarily all, query document combinations. And those judgments can usually either be binary, 1 or 0, or on a graded scale, for example, with 4 different judgment classes, and the higher the number, the more relevant the document is. The query source can vary wildly, so we can have handcrafted queries from experts for a set of documents that try to probe the collection as diverse and best as possible. Or we can use sampled queries, for example, from actual users, as is done in the MS Marco collection. And the document source is very task-specific in most cases. Although in general, I would say as a sort of theme for IR research, we focus a lot on well-parsed web text, news articles, Wikipedia articles, etc. Here is a short overview of existing IR datasets. And I want to start this overview by mentioning 2 annual annotation campaigns that actually produce each year new datasets and new judgments for existing collections. And those are TREC, the Text Retrieval Conference organized by NIST, which we'll hear about a bit more in a couple of minutes, and NTCIR, which is organized in Japan. Some example datasets include CORD-19, which is a very recent one, which has been developed during the COVID pandemic to help in scientific publication search with topics concerned with COVID. And then there is ClueWeb, which is a large web crawl data collection with some web searches associated with them. Then a very common collection in the last few decades, I have to say, is TREC-Robust 04, which is based on topical news article searches, and it has been influential for a very long time and used by IR researchers over and over again. And also news groups and Reuters news collections are mentionable. There is a brand new hub to get IR data, which is IR-Datasets, and you can check it out if you want to know about more existing IR collections. Now we'll turn to some of the most influential test collections from the last few years. And here I want to start with maybe the most influential one for everything concerned with neural ranking, and that is MS Marco, or the Microsoft Machine Reading Comprehension dataset. It's the first re-ranking dataset with a lot of training data. And I want to emphasize this a lot of training data, because now the scale of training and evaluation data becomes an issue, which is very much a luxury problem that IR researchers in most cases, especially in academia, didn't have before. The MS Marco dataset is created from real-world web search queries and passage-level answers from the Bing search engine. Its initial focus was on question-answer, the answer generation, and it's been released by Microsoft Research. It contains sparse judgments with labels for over 500,000 queries for training. The queries are selected with a very high occurrence count in Bing, so that it is impossible to leak personal data. And those sparse judgments are humanly annotated. However, we only have on average, a bit over 1 relevant judge documents per query. In my opinion, the MS Marco collection was a major contributor in the paradigm shift towards neural networks because it allowed academic researchers to participate in large-scale information retrieval that was only possible for web search company internal researchers before. And the leaderboard that was accompanying MS Marco, and still is very popular with over 100 entries already. And most neural IR papers nowadays make use of the MS Marco data in some form. Also, I want to mention including work from Google, which is very nice to see. And if you look closely here on this leaderboard screenshot and you squeeze, you can even see one of our entries here at the bottom on number 11. Let's look at a data example of MS Marco. So the training triples are as follows. We have a query and then our annotated relevant document, and usually we sample some non-relevant document that has something to do with the query but is not actually relevant. So here, what fruit is native to Australia, and the relevant document talks about a rare passion fruit that's native to Australia. But the non-relevant document talks about a fruit that's native to Africa, which would in fact not be a relevant answer. And in the re-ranking scenario, the evaluation tuples that we're looking at is as follows. So here we look at query document pairs, each come with an ID, so we can map it to the judgments. And a model now has to give a score of those two entities. Up until now, I talked about the MS Marco dataset as one thing, but in reality, it's two. So we have an MS Marco passage dataset, which is the one I was talking about until now. And we also have an additional MS Marco document collection, where researchers went back to the queries and judgments and URLs from the MS Marco passage and actually rescraped the web pages to include the full web page titles and URLs from the corresponding passages. There is a slight time mismatch and there is a non-perfect matching, but it's not a huge issue. And the documents here are very long, on average more than 2,000 words. So our plain text size actually increases from 3 gigabytes of plain text from the MS Marco passage collection to over 20 gigabytes for the documents, which gives us another challenge to work on. And I also want to mention that MS Marco does have limitations and we should be aware of them. So the way the MS Marco passages were sampled from the Bing index is we start with queries and then take the top 10 passages for each of those queries from Bing to create the passage corpus, which might make the task easier in comparison to a web scale index that has not those cookie cutter selections around the queries. And the focus is on natural language question style queries because the initial project was focused on this QA task. So it's not perfectly representative of a web search task. And it's only for the English language, so we don't have other language data in MS Marco. The sparse judgments can be a problem if we say, okay, we have only one judgment per query, which means that we probably miss a lot of additional relevant results if they're ranked higher. This can somewhat be mitigated with the large query count for evaluation to make the evaluation less noisy. Let's switch gears and look at a completely different way of generating IR datasets. And this is with the TREC Text Retrieval Conference, an annual event organized by NIST, which includes various tasks or TRECs with a challenge for participating systems. And those tasks are very much IR oriented, but with many interesting twists on domains and settings in news, podcast, medical, or web search. Many teams then try to solve this task and submit solutions or so-called runs in the summer months. And TREC has a budget and the expertise for annotations. So organizers create judgments for all participating systems, as many as they can. And then at the conference in November, everyone presents their approaches and gets the metrics from their runs, so the teams can connect. The TREC conference established many IR standards and test collections over the last decades. And it's just an awesome culture of information sharing and sort of a fun competition. One of those TREC tasks is the TREC Deep Learning track, which started in 2019 and continued since. It's based on MS Marco passage and document collections, and it's set up to evaluate a diverse set of systems trained on this large data. And the way it has been done is we select a small subset of MS Marco queries, 43 and 54, and then participants create runs for those queries. TREC pools the runs and creates as many graded judgments as possible per query. And it is a way to complement the sparse judgments from MS Marco. And the main results so far are that neural methods are as good as we thought before this track started. And sparse judgments are actually a good approximator for certain evaluations compared to the high quality dense judgments. If we look at the comparison between neural and traditional retrieval models, in the TREC 2020 edition, the passage task shows a very large spread between the best pre-trained language models and then the best neural model from scratch, as well as another large spread towards the traditional IR models. It's a strong validation of the neural hype, and we also have to note a few things about this plot on the left here. So first, the y-axis is a huge difference. So normally you would see very small gaps, but in this case we have very large gaps. And the top pre-trained language model runs are very slow ensembles. So they represent the highest achievable but not realistically deployable models. And in the document task, the results are sort of in the same direction, but with less of a spread. And the neural models from scratch do better than in the passage task. And the passage and document numbers are not directly comparable, so we can only compare inside a task. And my opinion here is the way in the document task is not that the spread here is not as big, is because the community invests more time and more focus on the passage task at the moment. If we compare sparse and dense judgments, we see that here on the left we have a plot comparing on the y-axis the dense TREC labels and on the x-axis the sparse MS Marco labels, and all the participating models are plotted for the 50 or so queries that we're using here. And we can see a clear correlation between sparse and dense judgments, although the small differences, especially at the top, shouldn't be used for definitive system ordering for so few queries. But it also shows that we can continue to use the sparse labels on their own. Now that we've seen what's out there, let's look at how to create our own test collection for specific scenarios and how to know what we don't know. One of the first choices you have to make for creating your own dataset is who creates the dataset. And every decision has trade-offs. Here is an initial assessment of pros and cons between doing it yourself or with your team versus hiring external annotators to do the task. For external annotators, you need to do recruitment, you need to have compensation, and you need to train or prepare workers for the task. All of those things you don't have to do if your team does it on its own. And the problem by doing it on its own is that it does not scale very well if you want a large or high scale of annotations. And here the external annotators can be able to scale very well. And the expertise might also differ. So for example, in the medical domain, you might be in need of hiring doctors and other expert annotators to actually look at the data that you, with your computer science background, might not understand. Then, before you start annotating, you have to create your task design. So you have to have a clear picture of what you want to accomplish and think about the caveats of the task you want to solve and how to handle them. Take a step back and look at, does it make sense what you planned? Definitely try it out yourself before continuing. And one crucial aspect of a good annotation workflow is to make the task as simple as possible or decompose complex tasks into smaller bits. This gives you less ambiguity, better agreement between annotators, and of course it's easier for annotators to understand a short description versus having to read a 20-page or so manual before starting, which is definitely not motivational. And a simple task is also easier to analyze afterwards, and the annotations, depending on the task, might even be used for more than one goal if we recombine them in different ways. Here is an example of such a clever task design by my colleague Markus Slavinger, in which he created FAQ annotations, where the answer catalog can have hundreds of entries, but is a very fixed set. And looking up this answer can be very time consuming. So the idea here in this efficient answer annotation was to annotate questions with the same intent as a group. And by grouping questions with an unsupervised semantic text similarity method, the group-wise average annotation time could be reduced to 25 seconds per entity versus 42 seconds if we do it one by one. So the result is a more efficient annotation. After you settled on a task design, the next step is to create task guidelines and examples for your annotators. And guidelines are a textual description of what the annotator should do. It's important that this description is clear to the overall goal and the individual tasks of the annotation. It should be short and concise, and very important is to incorporate examples for different scenarios so that it's practically demonstrated of what should be done. The next step is to conduct a test run to see if everything works. So does my setup work? Does the output data of the system is actually in the right format and contains all elements that I want? Do annotators understand the task? And is the resulting label quality sufficient, or are the test labels all over the place? If so, you might reconsider your task design and start from scratch. This can be performed on a small percentage of all samples and is also possible with some annotators or all annotators for a short while. After the test run, you can start your full-scale annotation campaign. And one way of conducting such an annotation campaign is by using crowdsourcing and marketplace platforms such as Amazon Mechanical Turk or Figure 8, which allow you to post tasks and workers then can decide if they want to complete them. You can set requirements on a country, a language, education level, etc. You can set how much you want to pay them, and it allows for a very large scale of annotations. So here, important to note is that scaling costs a lot of money and also the time to set up and supervise the annotations. With crowdsourcing, you need a lot of focus on quality control, as cheating is common, and the task design needs to be done so that random cheating is not possible, and a large number of majority voting is necessary, which drives up costs. Speaking of majority voting, it's a technique to let different annotators judge the same examples, which gives you a higher quality of the resulting data. On the other hand, you have to pay n times more cost in terms of effort. And with randomness, so that you don't actually create groups of annotators that could miss certain groups that only do bad judgments. And this allows us to monitor the quality of individual annotators. So here, some disagreement is always there, but if one always disagrees, this might warrant a more thorough investigation. And it also allows us to better understand the task that we want to solve. So how to interpret agreement ratios. Is the overall agreement high or is it low? The question now is how to evaluate the annotation quality. And we can measure the label quality of annotators based on their inter-annotation agreement if we utilize majority voting. But we can also base it on a few samples that are labeled by an expert and then subsequently labeled by all annotators. The inter-annotator agreement tells us if humans agree on the results, and the general agreement there is an important prerequisite for an algorithmic or machine learning solution, because if humans can't agree on a solution, how is the machine supposed to learn from that? And if you want to compute the inter-annotator agreement between two annotators, you usually use the Cohen's kappa. And if you have two or more annotators to compare, then you use Fleiss kappa. And the kappa result interpretation is somewhat subjective and always depends on the task what strong, moderate or weak agreement actually mean for you. Now, from those more general informations on how to create a dataset, we turn to a very IR specific technique, and that's called pooling. In information retrieval, we need systems to retrieve from a full, meaning a large collection of documents. Otherwise, we would be not modeling the real world conditions right. And of course, we can't annotate all documents per query, which would mean potentially millions of annotations for every single query, where most documents are not relevant. So we get retrieval models to help us. And retrieval systems, proven retrieval systems, create candidate documents for us to annotate. And here, if we use a diverse pool of different systems, we can then even reuse those pooled candidates. And this gives us confidence that we have at least some of the relevant results in those pooling results. And it allows us to drastically reduce the annotation time compared to conducting millions of annotations by hand. The pooling process is as follows. We gather a diverse set of retrieval models here in the 4 colors, and we index the same collection with each model. We then select a list of queries and repeat this pooling process. So for each query, we let each system retrieve their top ranked documents, passages, or elements. I'm using documents here as a term for all these subterms. Then, after retrieving this ranked list of documents, we choose a cutoff point, K, where we guarantee to include results per system. This is a very simple method that allows us to compare all those systems up to a depth of K. But of course, there are more complicated and improved methods created for pooling at various depths. But right now, we're going to keep it simple. Then, to create our pool, we remove duplicated entries. So this then actually makes pooling more annotation efficient than simply relying on a single system at a time, because we save annotation time by removing duplicates. And now those query document pairs can all be annotated. With this annotation task and the pairwise labeling, we now know for each of our pairs, or for every list, we know the label for the documents. And as the last step, after every pair is annotated, we of course map the labels back to all the duplicated documents to receive our full list per system. So now we can use the ranked list evaluation metrics we heard about in the evaluation crash course to compare our systems. Hooray! But what if let's say we did this annotation campaign a while ago, or someone else did it for us, and we want to create a new system that does things differently, and you want to reuse those annotations. You have to be aware of something called pool bias, that if a new system retrieves a new set of documents, very likely this set will include unjudged documents. So in that case, the missing documents have to be assumed non-relevant, which of course puts the new model at some disadvantage in comparison to the models who participated in the annotation campaign. If we want to annotate focusing on recall, we kind of need to know judgments for all, quote unquote, the relevant items, but we don't know which of the items is relevant beforehand. So the test collection depends on this pre-selection of documents, and relevant items might be missing because of vocabulary mismatch or other small details. So what we can do in this case is actively work on this problem with iterative annotation cycles and active learning, and the HiCall tool is such an annotation system that integrates active learning in an iterative query document pooling process. Or at least if our test collection is not prepared for such a high recall scenario, for example, if we use sparse judgments, we should be at least aware of those limitations when interpreting all our metric results. I now want to highlight some annotation work our group did in 2020, and this is FiRA, or fine-grained relevance annotations. And here we went back to the TREC deep learning TREC document ranking annotations and annotated every highly relevant document on a passage and word level, which gave us a total of 24,000 query passage pairs using 4 classes for graded relevance. I'd like to highlight some of our results here concerning with different relevance classes and majority voting. So keep in mind that every document overall in this evaluation, as judged by TREC, is relevant at some point. And what we find is that many passages in those relevant documents are not relevant, which gives us new intuitions for passage score aggregation techniques. And here on the left, you can see that majority voting is important, especially if we look at the 4-level graded relevance, as most relevant passages are not unanimously decided and there is some ambiguity. And this uncertainty of relevance is also highlighted in this case, where we selected some passages, here 2 for example, that are annotated by all our annotators, so we can qualitatively study the subjectivity of relevance annotations. So here in this case, most agree on the general relevance between the relevant or not relevant classes. However, if we look at the 4-level results, it's not that clear anymore. And the heat map of selected regions, so if a word is more saturated in green in the background, it means more annotators selected it as a relevant word. And in the upper example, we can see that the uncertainty of what is actually relevant in this passage is way higher than the uncertainty in the second passage, where it's pretty clear that only those 2 sentences are relevant to the query and the rest of the passage is not. Speaking of biases, one important aspect of all things data is to analyze biases and also analyze the downstream impact of existing bias in the data. Of course, there are many types of biases, and here in this lecture we only scratch the surface of research directions in this field. So taking biased text as input will very probably give you bias output representations. You might not be able to easily measure the bias, but it is there. And bias can take many forms, such as gender or racial bias. And it can have a decisive effect on people's lives, often and easily unnoticed by the responsible people. For example, if we employ machine learning models in hiring decisions or predictive policing or in recommendation algorithms that marginalize minorities, all those applications have a downstream effect of those machine learning models that are in the back end, and learned by biased data can produce dangerous outcomes. But we also are concerned with less dangerous forms of bias, such as learning to ignore certain positions of text in a document, which is a very technical form of a bias. Let's talk about a bit more about bias in word embeddings. Word embeddings are usually trained on large-scale unlabeled text. And for example, a common resource for that is the usually associated high-quality Wikipedia. And important here is to know that if the training data is biased, the vectors will be biased as well. And in this example on the right, we can see that when Word2Vec is trained on Wikipedia, the resulting vectors contain significant gender bias with female to male analogies associating certain stereotypical words more with the female label than the male he word. And the good thing about word embeddings is that because we only have one vector for one word in our vocabulary, we can make those comparisons and those analyses to find the bias in that way. Various methods have been proposed to debias word embeddings. However, we also have studies that show those debiasing methods might not be truly effective and only cover up the bias. In large language models, the bias becomes much more complicated to measure than in word embeddings. And recently, the so-called stochastic parrot paper and the subsequent refusal by Google to let it publish and all actions that followed created quite a stir in the community in early 2021. And I want to highlight this opinionated paper because it has a great survey of the state of the field, and it makes a lot of important points for researchers to think about going forward. So the authors argue that exploding dataset sizes in training large language models, including using outdated text, will result in unchecked biases. And if you apply static stopgap measures, such as removing documents that contain certain keywords, might hide minority communities and have an adverse effect counter to what they're actually employed for. And language models are only seemingly coherent, especially if they create text. So it's not true language understanding. And language models also amplify training bias in real-world use. The authors finally argued that we need a mindset that weaves responsibility and thinking about where to deploy certain systems in our whole research process. It is a great read, and I can only recommend that you take a look at the paper. Furthermore, if we look at ranking models and recommendation models and the social impact they can have, is always concerned with what those models are optimized for. So if, for example, you optimize a model for time spent on a platform, it's easy to let users fall down a rabbit hole because scandalous and click here to find the truth videos, etc. are more likely to keep you on the platform and thus generating more watch time. And if you look at the world as a whole, you have to be aware that, of course, there are many, many languages. And if you manually invest time in blocking English content or, for example, weird autocomplete content in English, it does not automatically translate to other languages. So this problem is, of course, not easily solvable, but we should be aware that it exists. Now, we turn to something a bit more technical and of course less dangerous, but still interesting. And this is the term position bias. So in a bag of words model, such as the traditional IR models we saw in the crash course on fundamentals, they don't know about word positions. So this problem doesn't exist there. But in most neural models, a term has positional information associated with it, which then can models learn to overemphasize this positional information if a bias on the position is in the data. It will be learned, which, for example, if you learn a bias on the start of a passage or a document, and you want to find or retrieve the same information later positioned in another passage or document, it puts this other passage at a disadvantage, even though it would contain the same information. So this is a problem for generalization, and also it shows somewhat a limitation of neural models, and I think we should be aware of that. This is different from the result position bias that is most often associated with the term position bias, where users tend to click on first results in a list of web search results, even if relevant ones are further down the list. Our group tried to find the answer for where is the passage level relevance, and we started off by observing a bias in the MS Marco QA data, where answers tend to involve words at the beginning of a passage. And remember, the MS Marco passage collection only contains one relevant judgment per query. So this bias directly follows the retrieval labels as well. And with FiRA, we conducted a rotation-based controlled experiment to see if we can replicate this phenomenon, although we have to have here a disclaimer that it's not on the same passages because we looked at the documents, but it's the same domain. And our results show that almost uniformly selected relevant words, and only in the rotation there is a slight drop around the corners where we did rotate the document or the passages. We now wanted to go ahead and see if we can detect this position bias in transformer-based models. And yes, we did actually find that in the TK model, which you will hear about more and as part of this course, where transformers use positional information of terms with an embedding, the influence of the position is trained. And here on the left you can see our plot with a cosine similarity between same term occurrences across passages, and on the x-axis we plot the position delta between those two occurrences that are compared across passages. And in the original training in red, you can see that the passage has a very the passage position has a very strong influence on the similarity of the same term, mind you. But if we debias the training data, here in blue we observe much less positional information as part of a contextualized vector. So finally, I want to extend this question and ask, where is the document level relevance? So where is the likelihood of relevant passages across a long document? And what we find here is that relevant passages are more likely to start at the beginning of a document, although it's definitely not exclusively for the first passage, and it also extends far behind in the tail of a document. So this keeps us giving new insights into how to design neural models that work with such a long text. To summarize this talk on test collections, I want you to take away that IR test collections are incomplete, and we must deal with the uncertainty that comes from that. Judgment pairs should use pooling of many diverse system results so that we might be able to reuse them. And finally, bias exists everywhere in different forms, and it's at least important to be aware of it, and even better to act according to this bias, so that it does not have negative effects on downstream applications. Thank you very much for your attention, and I hope you enjoyed this talk, and see you next time.